just pop them in the chat, or raise your hand, and Suzanne will keep an eye on that. I was doing a project with one of us a while ago, I think back end of last year, and then I found that this person put everything into a data frame. So we had a data frame filled with data frames, and even pickled models into a data frame. And I thought, well, so my background is in AI, but also software engineering. So it started to itch a little bit. Not everything is a data frame, and there is plenty of other opportunities to put data in, to deal with data, to manage your data. So we started thinking about this, and then we decided to put on a pizza session on this topic. So what this pizza session will not be is a full overview of all the kinds of data sets and all the kinds of ways of dealing with data. It's just well, not random, but it's an overview of how you can approach data if it's not just a tabular form. So slide 1, this is very much a data frame. Everyone can see the slides? I think I'm sharing, but I'm not sure.
Yes, I can see them.
Are they gone? So yes, very much a data frame. Also very much a data frame. We have a number of columns, some fields, some information in there. This is a data frame I'm sure everyone knows, the Iris data frame that comes with sklearn, scikit-learn, that we've all, I'm sure, played with very much a data frame too. But in real life, in reality, if you just open your eyes in the morning and you look around, most things are not a data frame. Most things are not a two-dimensional structure that have data in nice little columns. A stack of papers is not a data frame. Clouds in the sky are not a data frame. And when I say they are not a data frame, doesn't mean that you can't create a data frame that captures the essence of clouds in the sky. In fact, if you look at this image, it is just two-dimensional space of pixels. So in that respect, you can put everything in a data frame, but not everything does naturally fit into a data frame, because a one-by-one matrix of pixels doesn't tell you much. You can't really machine learn anything on that. Also, and we're going to have a look at supermarkets. Also, this, if you look at it, is not a data frame. It's not one by one. Yes, you have a bit of a structure here, but it's not strictly a data frame. It's not. So here you have shelves, you have positions on the shelf, you have a cooler at the bottom. There is a shelf on the left, etc. And then every package has a different size, a different quantity. Some are measured in numbers, some are measured in kilograms, some are measured in liters or milliliters. So real data, if you look at it, is messy. And finally, this is also not a data frame. It's a messy thing that you need to take care of to put into a structure. So what I have prepared is of course a Python notebook that I would like to walk you through, and then there is some code that we created on another project that I would also like to talk to you about. So what is a data frame? Every row stands on its own. Every row is a sample, is a data point. Every column belongs to that row. So every column has a meaning in respect of that row, and every row is a single observation. And a data frame is contains everything we need to know. There is no more information that is currently relevant for why we have this data frame. And most importantly, it's a homogeneous set. So they all have the same attributes. Some may be empty or missing, but if they're missing, there's a reason for that. And all the elements describe a member of the same class. So every row is like I said, is an observation, and they're all of the same class, the same thing. You wouldn't put dogs and airplanes in one data frame normally. So let's jump straight in. What is a data frame? And I've nicked this just from the web, just to refresh your memory a little bit. A data frame is a two-dimensional thing that we have, for instance, in Python, but R has data frames, Spark has data frames. It's a known concept, and usually they have two indexes, one at the top, which we call columns, and that array is a column index, and then one at vertically on the side, which is the index. And then we have cells, and every cell contains data in different, how you call it, in different types. So we have strings, we have categories, and we have numbers, either integer numbers or real numbers. And in this example, we only have real numbers. Now let me put something on the screen, and then I need to get number 2 here, something that I prepared. You should now see, and I'll open this on my laptop as well, but you should now see something that looks like a Jupyter notebook. Am I correct?
Yes, we do.
Okay, thank you. All right, and we're in the middle of this notebook, and we're sharing this notebook afterwards. So we'll put it on the Meetup platform. On the left, you see the cells. On the right, you see the output of that cell. And here I've created a data frame that has an inventory with some columns, and I've created some data types. Now, moving straight here, what I do is I create an inventory out of product placements, and the inventory has a number of columns, a category, a subcategory, some kind of ID, some kind of shelf or cooler, a position, a SKU, so that's the product identifier, and then a size amount, a size unit, and a price. And here on the right, you see how that data frame looks like. The standard data frame comes with our column headers, and then some kind of index on the left, which is by default just a a number. Now I've taken care about a number of things, and like I said, I'm a software engineer by training, so I feel very sorry if I see a location which is an integer, and I put it into a data frame and it turns into a float, because a location is an ID, is not a float, it's an integer. And in fact, I have to specifically tell dear good old pandas that actually I want this to be of a certain type, because it interprets it by default. It interprets it as a float, because yeah, a data frame is for making calculations. So what I do is I tell it these are my columns, and I tell it these are my data types. The first is a string, second is a string, and here I tell it this is an 16-bit sized data type for an integer, and the same for the second, for this column, etc. And I'll move this around a little bit. So this is how I tell it these are my data types. And then there is the asType method for a data frame that turns that data frame, or I can tell it these columns have these types, and it tries to put it into those types. Maybe for the real details, we're using pandas 1 here. So they've moved away from the standard NumPy NaN to something they call a pandas NA, and so here you see it says it looks a little bit different from what you maybe used to. All right, now let's have a look at this freaking index, because I am sure that whatever code you look at from someone that you know, or from someone you don't know, you just download, that code will be scattered with a reset index, because somehow we don't really understand and feel for this index. Where I think it's actually quite a nifty thing. So if you look at this, for instance, I create a location ID, and I do that by just sticking a couple of things together. I put together the location ID, and we'll look at the data later on. I put together something that is dependent on whether it's a shelf or a cooler, and the position within that container. And this is, I'm sure you can read this, where the shelf is NA, I take the cooler number, and if it's not NA, I take the shelf number. And that creates location IDs like this. So 30BO for a non-cooler, and here I have a for a cooler, and here I have a non-cooler 600-4-4, etc. So this location ID is an indicator that tells us exactly where in the shop, so what ID, but also what shelf and what position on that shelf, or what cooler, what position in that cooler the product is placed. And then I can use that to set an index, like I do here. Dataframe.setIndex location ID. I actually tell this thing that from now on, this is your index. So no longer it's just a 0 to 99, because I've got 100 placements in here. It is actually this ID. And why is that important? Well, I can then do all kinds of funny things about it with it. I'll show you in a minute. So location ID is an index, or even I can create what's called a multi-level index or a multi-index. So for instance, we have per product, we have category and subcategory. I can tell it here, set index to a list of a number of things, or a number of columns, cat and subcat, and it creates a multi-level index from this. And by doing that, I can now super fast select relevant rows. So for instance, the .xs operator will get me all the non-food rows very quickly. And it does that very elegantly because so non-food is a category. I can tell it that the key must be non-food. And you see, well, automatically it drops that column from the index and only retains. No, they don't need to be unique. No, that's cool. So they're not a unique, how you call it, key. They're an index. So it drops the category column from the index that we had here, only retains subcategory, but only of those that are non-food. And the cool thing about this, and for 100 rows, it doesn't really matter. But if you're 100,000 or even up to millions, creating an index enables you to really quickly select, make selections from that data set. By default, it looks at the first column of a multi-index, but here, for instance, we have told it I want to have all the cookies for the level subcategory, and here, boom, you have all the cookies that are in the data set. Obviously, with the category food, because yeah, it's a food stuff, right? Cookies. Now, so I love indexes, and I love the fact that you can actually group things together very easily. And so whenever I deal with data that I have in a data frame, I always think about what hangs together, what are the main identifiers that I want to put in my index, even a multi-level index. It also happens, for instance, if I want to calculate the mean size and price by subcategory of this thing, I obviously use the .group by, but since I have my data frame nicely ordered by category, I've set the index to be by category. I don't need to tell it these are the columns and then it needs to sort things and do all the grouping. No, I just tell it this is the level I want to group by, and boom, it's done. I have by subcategory, I have my mean price and mean size. Now, what if we want to get and this really gets me. This is the way that people normally do grouping, right? So I'm back to my old data frame, not the data frame that is created, but my old data frame, the full thing. Normally you would say, all right, I want to group by, in this case, position, take those two columns, size and price, take the average, or take the mean and yeah, drop the index. Now, hands up if you've done that before. It happens a lot, yeah. I see all kinds of hands going up. And how much I hate pandas because of the inconsistencies of the interface. there is actually a very smart way of doing it. Either stick it into an index and just group by level, like we do here, or tell group by not to return an index. It's as simple as that. In that case, it does exactly the same calculation, but leaves your value alone. See, the outcome is exactly the same, but in this case, it did not first create this freaking index here and then drop it. It just doesn't create it. It just does the grouping. All right, so that is the story about data frames and indexes. Now, I'm going to go back to, and when you get this sheet, you'll see that actually there's a whole bunch of stuff happening at the front, because not everything is a data frame. In fact, we've really pushed hard to put this into a data frame, because we have a whole domain out there, a whole real world that we hacked together and stuck into a data frame. What I've done is I've created this data built on a let's call it domain model. One of the cool things that we have with the modern versions of Python is something called a data class. Well, if you are into this field, you must know what a class is. It's a cool concept. A class is actually defines all your functionality, and then you have an instance of your class. And the funny thing about a data class is that it comes with boilerplate functionality. So let's look at this one, for instance. I've defined class product, and I told it these are your properties. So a product has a category, a subcategory, a SKU, needs cooling, yes or no. It has a size, a price, and some dimensions. Under the hood, because I told it this is actually a data class, under the hood it creates an init like this with all my friends. So cat, subcat, SKU, needs cooling, etc. And does a proper super init and self.cut equals cut, etc. Self.subcut is subcut. That's what it does for me under the hood. So I create an object that carries all the data elements that I need. Therefore it's called a data class. What I do is I overwrite the str, the string function, to create a nice printed version of this product whenever I get to print it. And I do the same for my shop location, which has an ID, a shop X and Y location. And then I say, well, actually, in that shop location, there could be two things. There's either a shelve or a cooler. So what I do is I create a shelve, which is a subclass of shop that just adds a shelf number and a position on that shelf. But I also add a cooler location, which is again a subclass of shop location that has a cooler ID and a position. And the funny thing, of course, is that the position on the shelf is just an integer. Position in a cooler, because it's 2D, I decided to have A, B, C, D, 1, 2, 3, 4. It's like a two-dimensional thing. And that's I made this up. But these are subclasses. So whatever is defined on this one will also be defined on its children, but this child has additional fields. Now that's a cool way of thinking about data, because it structures the thing you're thinking. It creates a domain model. It creates something that actually looks like the image that we've seen before. And then I have a product placement, which is nothing more than I have a product and a placement, and they hang together. This product is positioned in that spot. And then I've created some loops with loads of randomness to create my shop floor. It has an X and a Y ranging from 5 to 7. All my coolers are at X below 1, or X is 0. And they have a C and an L, A, B, C, and 0, 1. These are my locations. And I just put my shop locations in a long list. And if it's not X is 0, I create shop locations. Here they are cooler locations, and here they're shelf locations. So I create a set, or sorry, not a set, a list of shop locations. And if you look carefully, where am I? Here are my shop locations. Shelf locations, well, yeah, these are just random shelf locations. Same for products. I create a quick dictionary, food and non-food. Food has a list of stuff, and non-food has a list of stuff. I create SKUs from 1,000 to 1,100. I get a random category, a random subcategory from that category, a random choice of false and true, whether it needs cooling or not, etc., etc. Have a look when you need and one funny thing, if this product happens to need cooling, I put a C in front of the SKU, and if it doesn't, I just put the SKU in there. And it's just to make it harder to deal with this data. So if you look on the right here, you see C1000, C1001, and then 1002 is a product that is just happens to not need cooling. Okay, so here we have just 7 randomly created products. Now, the way of dealing with this, so I create a just this selection. I create a product, and this product has a number of features or a number of attributes. And since this is a data class, I can just add them to it. It's a real thing. It's an instance of the product class. Very different conceptually from just a row in a data frame. It is a real thing because I then start placing those products, and here, and those products are they're placed here. These are conceptually quite deep elements in the sense that a product is a full product and a placement is a full location. And the location is either a shelf location or a cooler, and they are both children of a shop location. So it's rather a complex component that we're looking at. And then we're back to where we started. Our inventory is just looping over all our product placements, and for all the columns, I can now pull from those product placements. And I do that like this. All right, I have a product placement P. Give me the product, and from that product, give me the category. From placement P, give me the product and give me the subcategory. From that placement, give me the placement ID, the placement shelf, if this happens to be a shelf location, else nothing. Give me the cooler if this happens to be a cooler, else nothing. Give me the position. They both have this, so I can call, I don't need to make that distinction. The SKU, and then the size, amount, and the unit, and the price. And then inventory is a nice little list of tuples that I created, and I can just create my data frame from it. So here I make the jump from a rather complex domain model into something that I want to deal with. And then I think I started off thinking that I want to, I don't know, calculate the dependency of price versus shelf location. Whether on the lower, I'm sure that's true, on the lower shelves, the prices are lower than in the middle, and then at the top they're also again lower. That is something that's I can imagine, and for that I need maybe a structure like this. If I want to know how many products can I fit on a shelf, I have the data in my domain model. I just need to create a different type of structure from it, a different data frame. So here I make one projection into my data science world. For another problem, I create another projection. One more thing that I want to talk to you about on data structure is this little friend. Now I know that you have experienced a categorical variable that has a typo. I know for certain that this has occurred to you. Hands up if it hasn't. See? Now, that is painful because all of a sudden you either have an extra additional category or your model fails. So whenever I think in domain world, I try to enumerate my my categories. And the way I do that is by just importing, I'll show you my imports. From enum, I import something called an int enum. And an int enum enables me to just list my categories and just number them. 2, 3, 4, 5. And this unit class, which is a subclass of int enum, I can then use to make sure that the only unit size unit I can give is either gram, kilogram, milliliter, or liter. And that's it. No typos, because there will only be one reference to this this little friend. And I really had to look if it's correctly spelled, and I'm still not sure. So then I can create a data class size unit that has an amount for the size and the unit of the size, which I then can use in my product, etc., etc. And then when I go to the projection,
Willem,
I can say,
there is
yes?
a question from Andrew. Is there an advantage in doing that over pandas categorical data types?
No. Well, there are two different worlds. So I do this in domain world, where I do the modeling of reality, and then when I put them into pandas, I can definitely tell it, well, actually, you use this column is now a categorical pandas category. But that's only at this point that's currently on the screen, where I do the projection from my domain world to my pandas data frame. Here I made it myself very easy to just say, well, actually this is a string. The cool thing is that I can, because I have a placement, that placement has a product, that product has a size, and from that size I want the amount in one column. That size also has a unit, And in that column, I want the name of that unit. Boom. And I know for certain that I won't have any typos in that name. Right, looking at time. Oh my God, we're not even we've not even started looking at other. So I think the story here is that you need to think about how does reality look like. So what are your data classes and how do they hang together? And then from that, so you have your data, and from that you can make a projection, because there's a couple of attributes of the domain data that are not used. So dimensions, for instance, they're not used in this exercise or in this challenge. The challenge here is, can I find a relation between price and location? If I want to see the density per shelf, then I might need other data that is in the domain model, but just isn't in my data science, in my data frame. Right. So, what if we were to look at this as were it a real database? Now, hands up if you've worked with SQL before. Yeah. Many. Almost everyone, right? Now, I have a love-hate relation with so for an assignment, you might get some data, for instance, several Excel sheets, create a domain model from that data, and then project it in data frames from visualizations. I like that approach very much. So whenever, one of the things I quite often do is if you get them in Excel or CSVs, I create my domain model per sheet. Because those sheets, they hang together, and then I create a domain model per sheet. Also, I can then just read them in as objects rather than rows in a data frame. So we all love and hate, or at least, we have some kind of relationship with databases. Why not? If you have your data in a columnar fashion, why not put it in a real database? Why does it need to be a data frame? Because if it's in a real database, I can actually talk SQL to it. I can actually run my SQL flex my SQL muscles. So there is this SQLite that comes with Python out of the box, and it's very simple to work with. You just open a connection to a database, and this in this case is a database file, and then there's many ways of doing it. I would say open a cursor, execute something. So in this case, I drop my product placements data frame table if it exists. I commit that, and then pandas is very helpful in enabling us to store a data frame through a connection to a database. So whenever you run this, and then I'm going to show you this one. This is a preview of the database, and that comes with what's it called, PyCharm. So in PyCharm, I can actually open my database, and here I see that there is a product placements data frame. And if I double click here, boom, there we are. It looks like a real data table. I have my shelf that is nil, if it's a cooler, my cooler ID, my position, which is a string, SKUs, etc., etc. The location ID I created. So that's kind of cool. Just a couple of lines, and I have it in a database. Now, how do I get back? This is presentation mode, so I need to still get used to that. I want here, and I will go back into presentation mode. Sorry, that was not as slick as I dreamt it last night. All right, so back to here. This is how you can quickly just put stuff into a database. There's one little trick. Again, I tell it this is an index because this is data frame by location ID. So that's the data frame I created right up here by setting the index like this. So I tell it this is the index, and then if you look carefully in the screen I just showed you, there is actually an index defined for that. It's not a unique index by default, so it's not like a key, but it is definitely indexed. So I can quickly select based on, in this case, location ID. Now getting things out, and now we're moving away from good data frame world. Getting things out, so select star from this table, and then just loop over all the rows that you receive, and here you go. You have all your rows as a tuple, nicely formatted with our location ID, the category, subcategory, and all my fields. None, and this is Python world, right? No pandas, no numpy, real proper plain Python. That means that I can do, I don't know, I can do my average price and average size by position in SQL. So I can read the output of this query, tell it that I want to be indexed by this this column, and I tell pandas to read this this query from this connection, i.e. this database, with a position as my index. Boom, same list again. Average price, average size, in plain old SQL. Now, dropping all of this, I can actually, and I'll invite you to read this at your leisure if you want. I can now create from my domain model. I can immediately create my database. I create a table products that has a SKU, which I now declare as a primary key. It has a category, subcategory, a boolean for whether it needs cooling or not, a size amount and a size unit, and a price. And I just loop over all my products and insert them into my table. So very similar for shop locations, and I just insert all of them into my table. Again, nothing pandas, real plain good old Python. And here finally I put the product SKU and the placement integer, the placement ID into my database. So let's see how that looks like. I go, where do I go? I go here, I go tool window, I go database, and then here product placement is my product SKU and placement ID. And if I have that, I can actually recreate my inventory by just joining these three tables. The product placements, which is PP, and PP SKU is from products, and PP placement is from shop locations, and I can create exactly the same world. And if I have this query, I can now create my my same inventory table, or sorry, data frame from this query, like this. Or if I really want to be smart, I can tell it to use those two columns as an index, and it comes out nice and fresh as an indexed data frame. The only thing that I haven't fixed yet is that it uses the, say, old way of expressing nonce. It uses the NumPy none rather than the new pandas NA. That's the only thing. All right, so any questions now? Looking at the time, yeah, we're doing fine. This is all fine, but what about using our storing things, not push them into tables? And really, I mean, I quickly went over it, but in fact, what we're doing here is not really nice. Well, we have this nice size class that has an amount and a unit, and we're basically splitting them up into two columns. So yeah, we're again we are yeah, harming reality. We're pushing reality into flat one by one dimensions. There is a concept where you so either you pickle everything into a big pickle file, and then you can pull out your list of complex option or say dictionary type data classes, or you use the shelve. Has anyone? Andrew is dropping. All right, thanks for joining, Andrew. Anyone used the shelve before? Hands up. Okay. So the shelve is like a persistent dictionary. And what I mean is, we all know a dictionary, and we'll have a proper look at how to use dictionaries later on. A dictionary that has a key value concept. Shelve is like a persistent dictionary, and it comes with Python. It's nothing that you need to install. It's standard out of the box again. And what it means is it is a like a database. So you open it as you would do a SQLite database. You can open the shelf, and in this instance, I just put my data objects onto the shelf. All it needs, like a dictionary, it needs a key as onto which you store the object, and then you can assign the object to it. So what I do here is I create a counter, an itertools counter. Itertools counter is just how you call it, iterator for an ID. So every time you call next, you get the next number. Just to quickly print these little numbers here. And then there is a function called asDict. Now that is, I would say, really awesome. If you look closely from, I think, 3.7, Python 3.7, you have these data classes. We have the decorator data class. There's also a function called asDict. The cool thing is that whatever you stick into a data class can very simply be transformed into a dictionary, and vice versa. So anything you want to hand off to someone else who doesn't know about your domain model, but knows about dictionaries, you can create. So our shelve doesn't know about data classes, but it knows about dictionaries. So what I do is I create the locator, which is a property of every placement, and this is the location ID, and I put my object in that position of the shelf. And then, because this is then closed, the context is closed, the file is closed, I have a file that I can then reopen and deal with it as were it a dictionary. I'll show you the file. It actually lives. How do I do that? Tools, window, project. Here you are, my shelf database, and I'll delete that for now. Save, yeah. Okay. Let me run this. Boom. Refresh. There we are. Here is the myshelf.db file, just the name that I gave it myself. And from that, I can just retrieve it. So I can run this with shelf.open this and this as my shelf. I can just address the shelf as if it is a what you call it, a dictionary. So I can look up any object that I put in there based on the key that I gave when I stored it. So very handy little thing. Because the cool thing is that I can store not a wrangled version of the truth, but I can store the real data domain model into my database. Okay, now why do I like dictionaries? I will tell you a story. A while ago, we had a project where we had the following challenge. And now I'm just starting on my laptop because I can only run it on my laptop. 0. Right, back to the slides. So we've seen this, we've seen this, we've seen this, we've seen this. Yeah. All right. The power of the dictionary. All right. Once upon a time, we had a project that looked at patient flow in a hospital. And we wanted to model those patient flows. And we had a whole lot of historical data. And you need to know that in a hospital, a patient gets admitted, then they either move to a ward or they go immediately into the theater, the operating theater. If they're on ward, they can either go to another ward or be discharged, so they go home, or they go into the theater. And there's a couple of more steps in between. When you're done with your operation, you either go in recovery back to the ward, in recovery discharge, or if you die at the slab, you are in theater, you don't need the recovery, you are discharged straight away. So that's kind of how a hospital works. And we had a whole lot of historical data around this, where we knew exactly when patients went from one state to another. The question we had is, can we somehow model how long it would take each of those transitions to be made? So, for instance, one interesting one obviously is, if you're in theater, how long does the operation take? Or how long does it take before you move from theater to recovery? And then obviously it's pretty straightforward, right? You just look at the data, you look at the distribution of that time, and maybe you even fit a distribution on it, and then you have a good sample set of that occurrence from theater to recovery. What we then found, if you do that over the whole group, important to know is, for every patient we had age, gender, all kinds of attributes that told us, and when it happened in the day and when it happened in the week, that state transition. So we have all kinds of attributes for the patient. Now you can imagine that if you look at say operating time, you can create, and that's the red one, you can create a distribution like this, and this is from that project. And that distribution tells you that most of them are just under 50 minutes, but we have a long tail, and yeah, some even are 0 minutes, quite a big chunk in fact. That doesn't tell you much. It tells you that in general, this is the profile how people move through the theater. Okay, fine, but we want to be a little bit more specific. What happens if you are a young person? Does it also look like this? What happens if you have a certain surgery to be done? Does it take longer or shorter? And what we found is that if you make certain splits in your data set, you can actually find two different distributions. So the blue and the purple ones are two different distributions. The blue one is, obviously most of them are much shorter, and the purple one, most of them are a tad longer, maybe up to 90 minutes. The question we had is, what is the most important feature that splits this group into the blue and the purple ones? And in fact, can we find almost like a decision tree that tells us something like this? So we are looking at the state transition from in theater to in recovery, and we found that if the age is less than 47 and is early in the week, but they're younger than 25, then it looks like this, and this is just a random Weibull function. If they're over 25, it looks like this. And if it's later in the week, you have a further, etc., etc. And if they're over 47, then it makes sense to look at the specialism. If it's not surgery, it looks like this. If it's surgery, it looks like this. Now, this concept of a set like this also doesn't really fit into a data frame. So what did we do? And I'm going to steal the screen from my laptop. I need to first dial into this meeting. Sorry. Again, not as slick as I was hoping. Join now. And now I can share my laptop's screen, where I wanted to show you this. not this. Sorry, guys. Share. This. Yes. It takes a couple of months to get used to this. Ah, okay, it doesn't like presentation mode. That's why it, I need to share the whole screen then. Yes. All right, so what we did is we created, and I won't be sharing this code, but I can walk you through it. We created a script that essentially tries every split it can make. Like, yeah, how did you work out where to make those splits? Exactly, I was going to get there. So what I do is we look at all the possible features, and per feature we look at all the possible split points. So we look at what's the, if it's like age, for instance, we look at the category age, and then for all the possible ages, so we look at the minimum, we look at the maximum, and we say, all right, let's divide it in 100 slots. And then we just test out what happens if we split all at, I don't know, 12 years of age, 30 years of age, 40 years of age. And we split the data set into 2 bits. And for 1 bit, we try to fit a distribution. For the other half, we also fit a distribution, and then we look at the entropy or say the disperseness of these 2 data sets distributions. So we look at how far are these apart, and that's the entropy, because that will tell us the split point. So it's brute force. We just try out all the combinations per split point. So we brute force all the combinations, and then we find those split points where the distributions are as far apart as possible. And then we go 1 level deeper, and we do the same thing again. That's fine, and it works, and we've parallelized the hell out of it. And it runs for, I don't know, 20 minutes or so, and then we're done. But it's called a tree, not without a reason, because the output then looks like this. The output looks like, we've stored it as a JSON file. The output looks like this. So here we have this straight transition from patient in theater to patient in recovery. We had just under 14,000 in that data set. Across the whole data set, we find that a Wald distribution with these 2 arguments actually has a MSE of pretty good. So it's a good fit of this distribution. But if we then split it by age, which is a numeric split point, at left is equal, less than or equal to 47.2. We have 2 children. The people that have an age lower than this, of which we had just over 5,000 folks. With this distribution, a gamma distribution with these arguments, with a pretty good MSE on the one hand side. On the other hand, we have 8671 people with, again, a Wald distribution with these 2 distributions and an okay MSE. Oh, but if we further split this one, and I'll open children here. No. Here we go. Then we find that if it's early in the week, we have just under 4,000 people with a gamma distribution with an okay MSE. So we say, oh, and then we have another split point, etc., etc. Now, this is data that hangs together. It is a real-world description, but it doesn't fit in a data frame. It does not fit in a data frame. In fact, what we did is we stored this as a sorry, as a JSON object, and then we created a funny script that takes this JSON and generates Python from this. So the best divergence.py, that's the derivation of the tree. And here we have code that is generated that has all these distributions as a big, you call it a dictionary. And we then have a function, select distribution from this state to this state for a particular agent, a patient. And then we have, if the patient goes from in theater to recovering, this is the generated Python. So we have our whole decision tree from JSON transformed into plain old Python. And it returns the distribution such and so, because that belongs to people that are under 47. It's early in the week. They're in fact under 25. Then this is the distribution you should use. If they're over 25, then if it's a planned anesthetic, and then this is the distribution. If not, sorry, if it's not a planned anesthetic, then this is the distribution. If it is, then etc., etc. So from that JSON file, we now created a plain old Python that we can then incorporate, import into our simulation model, and just call this function. With a certain patient, give me the distribution, and it would just return the distribution that makes sense. Now, how cool is that? The only point where we did some weird stuff with a data frame is when we ingest the data. Here we ingest, and we just stored this pandas thing as a big pickle file. That's where, and here we do the proper data selection from just as a data frame. Some type finagling, and here we go. Drop duplicates, also very underrated or overrated function. If you have duplicates, there's something wrong, and that's the only point where we use data frames. All the rest is not a data frame. Like I said, this is not a data frame. In fact, this is a tree, and in fact, this is an object, a dictionary, and in our case, a tree-shaped dictionary. Cool. Just as an example of how you can use... Hello? Right. I've muted Carlos, if that's okay. Right. Final thing that I wanted to share with you is, and I'm back to my screen. I think I'm back to my screen. Oh, I can see that on my laptop now. Exit presentation mode. I should be sharing my screen now. Let me try again. Yes. Okay, one more thing that I would like to talk to you about. We've looked at the database, and when I say database, people always think about something that looks like a data frame, or a table looks very similar to a data frame. There is a plenitude of different types of databases out there, all in the range of NoSQL-esque databases. And what I would like to talk to you about is something called Couchdb. Couchdb, and I'll show you this screen, which has a browser on it. Couchdb is a document store, or how you call it, a document store. So what I can do is I can store objects in it. So, and an object looks like this, very similar to how you call them, a dictionary, stored as were it stored in JSON. And obviously Couchdb is a little bit more smart than just to use to store them as JSONs. That is the database side of it, and we'll have a proper look at that later on. Let's first go back to this screen and see how we can put stuff into our Couchdb. And I'm a little bit worried about the lengthy error message here, but let's see if it runs. I'm going to run this cell. I'm going to import shelve because I'm going to read the data from our shelve, and I'm going to create our server connection. And here I can see Couchdb says welcome, and I'm an Apache software foundation. Access is ready. Yada yada yada. So we have a live connection. I then ask from my server, give me this database, server.database name. If that fails, with a not found error, just create it. So I run this, boom, it's done. And now I have a database. Let's have a look at this one. It doesn't refresh, so yeah, here we are. Pizza, not a data frame. No documents in there. I can put a document in there manually, but let's do that through some code. So it now created a fresh database for me. And then when I run this script, it opens up my shelf, runs through all the items in the shelf with the tuples index, or key actually, and value. Let's print them out as a dictionary, just for argument's sake. Create a document from them, and that's as simple as, remember, these are data objects, so I can just create a dictionary from it. Couchdb expects something called _ID as the key for a document, and I just create get locator. Remember, this V is not a data frame, no. It's in fact an object that I get from my shelf, because remember we put them in here just a minute ago, and these are proper objects, not some data stuff, data frame stuff. So I can talk to them as were they are still in real domain objects, not a projection of them. So from this object I get the placement. And from that placement, I get my locator. And I call that is going to be my ID. And then I save it into the database. Now let's run this. Oh, and it's done. Let's have a look. Like I said, this doesn't refresh, so refresh. That doesn't look good, does it? No, there's nothing in there. Oh, that's why it went so quick. Let's first put them in there. I ran this last night and then it worked. Honest. Oh, hang on. Here, it stored them. I was looking at the wrong cell. Let's see if I can get them back out. That works. Now let's see if I can store them. There we go. So here it printed. I should have known this because it prints the index or the key, a counter, and the actual object as a dictionary. So now, if I go back to here and I do a refresh, I have 100 documents in my database. Here we go. These are the objects I have in this database with the key nicely ordered. Yeah, they're strings, so they're funnily ordered, but they are ordered. And if I click on this, here we are. The beauty of my domain model, all fetched into an object, into a dictionary, stored in this funny database. So I now have a database full of my object, product placements. Product placement has a product. Here we are. And the actual placement. And here I have a placement with a shelve. And let's look here. This is again a shelf. And here we have a placement which is a cooler. Now, how cool is that? And if I want to run some queries, I can say, all right, on this database, run me a query that has a cooler greater than there won't be any coolers greater than 1. Nothing, but get me a cooler that has 0. Yes, it's not cooler, it's go back to my data. It's actually placement.cooler. And here we are. Here I have all my objects that are in a cooler. See? Now, how do I run queries on this? So how cool is this? Hands up if this is cool. Thank you. So what I really think is really cool about this is that we have our domain model. We've stored our objects in a file as domain objects. We retrieved them, persisted them into a database, and they still are domain objects. It isn't a data frame. I can create a data frame from it if I need to, but only for a specific particular case. Here I have my domain model persisted into something that's quite flexible. Remember, we have coolers and we have shelves, and they have slightly different attributes. Here we have the coolers, and they have cooler with some number, and a position that is an integer. Now let's see. So let's have a look at all the shelves. Here are all the shelves 0. They have a position which is not a string, but an integer. So not only do I have something that is a representation of my domain, everything that's unique to that domain pertains into this object. Then one final thing is, how do you actually query this? Because it's not simple select this. Good thing about Couch is that it scales from essentially from real big data, where you have a cluster of Couch databases that are continuously synced, all the way down to something called Couchdb, which you can run on your phone. And they have a concept of master-master synchronization. So one document, this is called a document, one object in one database can be kept in sync with that same object in any of the other connected versions of that database. So whenever you make a change in one, eventually it will trickle through to all the other databases. So that's kind of cool. So that means that if you have an app that uses data, your database will be automatically synced with the master database in the cloud somewhere. I see, Ger, you have your hand up. Is that a question, or are you overwhelmed by the coolness of this? Overwhelmedness. So how do you query this? You query this using either a Mongo query, which is it takes a bit getting used to, because you have a selector and then you need to basically create your query using some funny JSON format. But we also can create a design document. So let's create a design document, not this way. Let's say I want a new view of my data. Now, who in this group is aware or has worked with, say, Mapreduce? Hands up. Okay, yeah, some folks. So Mapreduce, Mapreduce is a concept that was introduced by the Google guys when they started doing their Google stuff. It means that if anything that you, any process, any data wrangling that you can do in a consecutive number of map and reduce steps can be parallelized. And what it means, map means I have my object and I map it to something else, a derivative of that. And reduce is, and that something else, sorry, that something else has two things, mainly a key and a value. And then the reduce step gets all the objects or all the values with the same key and reduces that. So for instance, if word count is the perfect example, you have an object that has a word, you map that to word with 1, and then the reducer basically sums up all the values that come with the same word, and so you do word count. And the cool thing about Mapreduce is that it scales because every map is singular. It only looks at one object and it maps that to a key value. And every reduce is singular into it only looks at one set of keys, one set of objects with the same key. So also parallelizable, very simple parallelizable. So whenever you look at big data stuff, it's very often that you run into Mapreduce concepts, and that's also what's used here. So whenever I want to do a query in Couch, I create a map function. Let's do that first. So I create a design document, and let's say that I want to only select all my shelves, and I call it only shelves. And that means, and this is JavaScript, that if this, so this is something I need to do for each and every document. If this document dot position has a shelf, I think there was a question there. No, if it has that shelf, I emit it, and let's emit the document dot underscore ID and the actual document. All right. So if this thing exists, then I emit it, else I won't. I just ignore it. And I do this for every document. Boom. Now I have a query that if I click it, shows me all the shelves. And obviously it doesn't work. Why doesn't it work? It's not position, it's placement. I made a mistake. I go back here, edit, placement, dot shelf, save, boom. Now, here I have the keys, which is the ID, and the values, which is the entire document. So whenever, Meg, thanks for joining, bye-bye. So here I have a shelf placement and another shelf placement, and I can now use this view because I know that whenever I call this view, I only get my shelf placements. Obviously, this is kind of straightforward. The cool thing is that this is not a view that is run whenever I click it. No, this is now persisted. So whenever a new document arrives, Couchdb keeps track of new documents. We don't know those yet. We don't know whether they are passing or not this particular view. As soon as this view is called from outside, it takes all the stuff all the output that is certain to be part of the shelves section, and then only looks at the new documents that haven't been touched before to pass them through this selection function, and then remembers that. So whenever I create a new document, it will persist the output of these map functions. And whenever the document is changed, it forgets it. So whenever the view is then called later on, it will rerun that for only the changed and new documents. Now that is kind of cool because that makes it very quick. Yes, it takes loads of storage because all the outputs, and obviously it doesn't store it as verbose as you see here, but all the outputs are stored in the database. But I can go a little bit further. If I want to, for instance, count, I can now also add a reduce function. Now, let me pause here. Are there any questions? Okay, if not, so we now have a map function. Let's add a straightforward reduce function, and there's a built-in _count function that we can save. So saved it. Nothing really happens unless I tell this query to also run the reduce function. How secure is Couch? Can we use it for client data? I'll get back to that, Justin. So I've told this query engine to also run the reduce function. And now I have a count for every key. So this key may not be so interesting. So let's go back. Let's not output the document ID, but let's have a look. Oh, sorry. Let's have a look. Let's output the category. So how many food items do we have, or how many items do we have on a shelf per category? So I go back to my view and I tell the function, if we have a shelf item, output document.product.category cut, and output the document itself. Oh, and we want to reduce that with a count. Save. Now we see this is the ID of the document, and we see those keys, and we see food and non-food. If I now switch on the reduce function, boom, I see we have 20 on the 20 shelved items on food and 17 on non-food. Now, how cool is that? And it's persisted. It is persisted in the database. Now, a question from Justin is, how secure is Couchdb? Can we use it for client data? Yeah, so Couch, it runs on my desktop here. I'll show you somewhere. Yeah, here this is the log of Couchdb. So it runs. Currently, we're talking to it using using HTTP, so not very secure, but you can secure the connection through HTTPS. Yeah, it is. You can just run it on any cloud box. So can we use it for client data? Sure, but not. Yeah, you need to take measures around it. So talk to it over a secure line, and there's a whole authentication and authorization concept in the database. If you look closely here, I open the connection with username password in the connect string. Obviously, that is not so very secure because here I have my username and password, and not a very clever password even, just in my code. But that is just because I was getting tired last night. So yes, it's pretty secure as long as you take the measures around it. Does that answer your question, Justin? Well, let me know if it doesn't. No problem. And yeah, we can have more fun with Mapreduce functions. What I really like about this is that we have now moved away from data frames and simple tables. We've now moved into, can I persist my domain in a database, or something that really persists stuff, either in a shelf using Python, or in something as big as Couchdb. That scales dramatically. So we're using this to store hundreds of thousands of documents across a three box cluster with loads of storage, and it remains persistent. So every document that comes in, as soon as you run a query, it only looks at the new documents. The old documents that haven't changed, they're already indexed. They are already, the output of that part of the query is already there. And because it's Mapreduce, it parallelizes very, very nicely. So that is the story. And let me see if I have any slides left. But I think this is, we're going to open it up for further questions, but this, I think, we have seen that not everything is a database. Sorry, a data frame. Yeah, this is. I was going to talk to this slide. Just this is something I dreaded when I looked at it. If you look closely here, we read some CSV. CSV horrible because it's always wrong and always hard to deal with. And then for every case in that thing, we just get another CSV and put that whole data frame into one cell of the original data frame. And that's just because, yeah, reality isn't one dimension or two-dimensional. We've looked at exploding this. Yeah, don't you hate it when Python does this? Why? Because computers are not very good at maths, I would say. So we looked at this. We looked at this, something that is in a tree rather than a dictionary, like this. And then we looked at Couchdb. So I'm going to open the floor for questions. Okay, no more questions, then we're done. I hope you liked it. I hoped to not. I'm sure I've not told you everything there is to know about other ways of looking at data. I hope that I have told you that or explained to you that it's good to think about the domain, and actually Python helps you there with this data class thing that are easily translated into dictionaries you can store in a shelve. But if you then have your domain, you can map it into or project it into a data frame as and when you want. And there is other ways of persisting data. Will we make the slides available? Yes, Carlos, we will. We're also recording, so we're going to look at can we store that on somewhere as well. And that's it. So I hope you liked it. We'll be sending out an invite for the next pizza session in a couple of weeks' time. Also, if you think, actually, I want to also talk about a subject that's dear to my heart, that's really technical, let us know. Reach out to Suzanne or us on the Meetup platform, because we're always on the look for interesting subjects. All right, thanks a lot.
Willem.
Have a great weekend, and talk to you guys later.
Thanks, Willem.
Thanks, Willem.
Good weekend.
Thank you.
Excellent.
Bye.
Thank you. Have a nice weekend.
Thank you.
Bye.
Thanks, Willem.